Good afternoon, average engineers. Today I am going to do a talk about Delta Lake and AWS Lambda. I gave this talk to the Delta Lake community recently. I can put a link to that official talk in the notes of this YouTube channel. I thought I would just do a shortened version of that talk here on YouTube for you guys and see what you think. So this will be kind of off the cuff. We'll see where it goes. Hopefully you can learn something. So really this talk is about one I gave to the Delta Lake community, and it's really about using AWS Lambda as a serverless technology to interact with your lakehouse in Databricks or otherwise using Delta Lake, and how you don't always need to use Spark, but you can use things like AWS Lambda and tools like DuckDB, Polars, Daft, etc. to work with your lakehouse without having to use Spark. So that's kind of what this talk is about. So where do you start? So when we're talking about AWS Lambda and Delta Lake, it's important to start the discussion about where we came from, like the data warehouse, and where we stopped for a little bit, the data lake, and then where we ended up, the lakehouse. I think that historical piece is a good thing to talk about because people will be people. We get stuck in certain ways of doing things, so understanding how we got to where we're at goes a long ways to explain why people think they have to use Spark to interact with their lakehouse when they really don't. So the takeaway from this talk is really don't be a lemming, don't follow everyone else, think outside the box, have more than one tool in your tool chain and your tool belt, whatever. When you're working with a lakehouse, it doesn't always have to be Spark. You can use many things like DuckDB, Polars, Daft, etc. And we'll show you how to do that with an AWS Lambda serverless architecture, which is super cheap and fast. So when we talk about the history of data, basically we have three eras. The data warehouse area, which is kind of classic relational databases, Oracle, SQL Server, Postgres, MySQL, etc. You had the data lakes that came after that, where people just dumped lots of Parquet, CSV, JSON files, whatever. They just ended up in S3 somewhere, and it was kind of like a middle ground. And then eventually we ended up with a lakehouse with things like Delta Lake, Hootie, Apache Iceberg, and it's kind of the best of all the worlds. That's kind of the history over the last 20 years. When we talk about data warehouses and where we're at today with a lakehouse, a lot of people use Spark, and there's a lot of historical reasons for that. It's also a scalable tool that works well. But back in the day, you basically had two options. You could have, if you had to do a warehouse that was on SQL Server or MySQL or Postgres, and then you had like this other world of data lakes where you had Spark and Hadoop back in the day, and there was kind of like no crossover between the two. You either were on one stack or the other, either with the small data on a relational database, or you had to go Spark on some custom Hadoop installation with HDFS or something to get big data workloads. That's how a lot of people had to operate for a long time before we got to where we are today. The problem with those old data warehouses is they just weren't very scalable. There's a lot of vendor lock-in. They were brittle. Things like SSIS, maybe data services if it's SAP, or maybe you're just writing some custom Python if you were working with Postgres or something. There wasn't really any good in between products. You're either using that or you're using maybe a Spark cluster that you installed yourself with HDFS and some cluster yourself somewhere, and it was just a real pain. There wasn't really, this was before Databricks or Snowflake or anybody was around. But at some point we got to the point where Apache Spark was used for everything. We were kind of seeing technologies come out like AWS Glue, Redshift, EMR, things like that. People were trying to make Spark easier to use for a good reason, and basically everybody got rid of pandas and we just started using Spark across the board for everything, a single tool for everything. And then of course we ended up in this land where we're in a lakehouse architecture with things like Delta Lake, where now we have ACID, CRUD, all these nice schema evolutions, everything inside a lakehouse. So it's kind of like the best of the data warehouse, the classic data warehouse, and the data lake put together, and now we have a lake house, and people have been using Spark with that lake house forever without even thinking that they could use something else. So that's kind of what we're going to look at today, is getting rid of Spark when you're talking about the lake house. You don't need Spark. So basically it's a different mindset when you're approaching these sort of problems. That there's other options like AWS Lambda, we'll look at that. It's a simple, low cost, and fast tool to use, and you can basically combine it with stuff like DuckDB, Daft, Polars, Rust, or whatever, Python if you want. And it really makes for a great tool stack because the architecture complexity is low because it's serverless. It's an AWS Lambda. And these tools like DuckDB or Polars, they're just pip installed they're just pip installed packages. And some of them, like the Daft and Polars, are backed by Rust, so they're super fast. And so it just makes a great option for working with your lakehouse. And you don't really need to use Spark if you don't have to. This isn't really about AWS Lambda, but I just want to take a second to talk about AWS Lambda. There's plenty of pre-built runtimes that AWS puts out for the Lambdas for Python, Rust, whatever, pretty much everything under the sun. They have about a 15-minute max runtime, and they can max out at about 10 gigabytes of memory. You can trigger Lambdas many different ways. And it's really a mindset shift of thinking about from that Spark mindset of I have to process everything at once to maybe processing one file at a time or processing files in chunks. And you can easily process big data with AWS Lambda as long as you just think about ingesting that data a little bit differently and get out of that Spark mindset. Also, Lambdas will work great with Docker, especially with ECR. If you're in AWS, you can build Docker images, pushing them out to ECR and Elastic Container Registry, and they integrate really well with Lambda, and everything's kind of packaged. So you can package your code, everything you need right inside a Docker image, and use it to run your Lambda. It's really simple, and it's easy to automate that process. And again, we're thinking about overhead here. This is a whole idea. You've got Spark, its complexity and overhead is very high, and you've got Lambda. It's very small and easy. So leave Spark for the middle set of your data pipelines where you're crunching terabytes and hundreds of terabytes of data. Leave Spark in the middle, but you're thinking about the front end and the back end of these processes where you're taking data into the system, into the lakehouse, and data coming out of the lakehouse. You can think about using Lambda. It's a great tool because it's fast, small, and easy, and you can just take a data byte at a time as it comes in and maybe leave Spark in the middle. This is just an example of how easy it is to build a Docker image. This is an example of the Duck Delta image that I packaged. I'll show you the code that I packaged up to run DuckDB on Delta Lake, and I just kind of packaged everything up in this Docker container. I'll show you that Docker image in a little bit, but this just shows you how easy it is to build an image and then push it out into ECR for use of the Lambda. Just a couple lines of code. Anybody can do it. I'm going to jump over to my AWS account, and I just wanted to show you I have my ECR, and I've got a couple different ECR images that I've pushed out for the different tools we're going to look at: Daft, DuckDB, Polars, and Python Rust. It's really easy to build out and push. You saw the commands to push out these ECR images. If I jump over, we can go to my Lambdas. If I put Delta in here, you can see I've got 4 Lambdas that kind of correspond to those ECR images. One for Polars, one for DuckDB, one for Daft, one for Python. And the Lambdas are really super low overhead. You can just add a trigger to any of them. We'll talk about that later. But they're just tied to my Docker image. It's really low overhead. So let's talk about DuckDB first. Everybody knows DuckDB. It's super fast, and they provide Delta Scan to read Delta Lake tables. You can interact with Delta Lake tables. And they also just released a new, extension that you can start to work with Unity Catalog Delta Lake tables. But either way, you can interact with any Delta Lake tables as long as you have a storage URI for it, and it's pretty sweet. So we're gonna do a real life pipeline here that I built on Lambda, and it's basically, the idea is we're getting a CSV file that drops into S3, which triggers our Lambda that has our DuckDB code. That DuckDB code does 2 things. It processes that data and pushes that data to basically like a raw landing zone in a Delta Lake table, maybe a bronze layer you could call that. Just some of that raw data out of the CSV file, but then it also writes to a cumulative table where it actually has to sum up some of the records for that day, for that model. We'll look at the code, and then it writes it to a cumulative table. So it's a pretty normal data pipeline where we have a file landing in our lakehouse, or landing in a raw staging. We need to, like in a raw place in S3 or some cloud storage, we need to take DuckDB code, read that, transform the data, and then push it into our lakehouse in the form of a bronze layer, and then maybe like a cumulative layer, more like a silver layer. This is what the data looks like. It's data from Backblaze. They have a hard drive data set that's free, available to look at. It's basically just a bunch of data from data centers about hard drives that have failed or not. So it's got like a date, the model of the hard drive, how big it is, blah, 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 and then if it failed or not, etc. And we're going to push that data using DuckDB into a raw table and then into a cumulative table. I just want to show you the Docker file first. Like we talked about, this Docker file is super simple, and this is what we pushed up to ECR and are using our Lambda. Real easy, of course. Lambda provides a Python layer image already for us to use. We just push in some secrets, copy over, pip install some requirements, aka duckdb, copy our files over, and voila, that's all the Docker images. The ECR image using that Lambda is super simple and straightforward, which is good. We like simple solutions. So this is the actual DuckDB code to interact and do that data pipeline we just talked about. We have two Delta Lake tables, one for the raw, one for the cumulative that we already talked about. This DuckDB code is pretty simple. Just have to install a couple things. If you're familiar with DuckDB, sometimes you have to do that. In my case, I'm just preparing the ability to talk to S3 and have AWS credentials. And what you can see here is I'm reading the CSV file, and this is all inside a Lambda with a trigger. If we go over here, this is the trigger that points to a bucket, and it says if a file lands here in this bucket, go ahead and trigger this Lambda, which we're looking at right now. Sorry, I clicked out of that. If this file lands here, we'll just trigger this Lambda. This is a Lambda code, and obviously the entry point is the key in the bucket that gets sent on the trigger. So we can read that CSV file from DuckDB, just saying, hey, and the file actually has like 200 headers or something. We're just getting a subset of those headers. We're saying, hey, give me this headers from this CSV file located in S3. DuckDB does that no problem. We just copied into a table called data. We can pull that DuckDB data to an arrow data frame, and we can write it out to Delta Lake into that location that we had up here, which is basically our raw layer in DuckDB, or in Delta Lake, just like our raw bronze layer, and it goes ahead and it reads that data and shoves it into that spot. The next part of our basically pipeline, as we said, we wanted to have a cumulative table, and that basically that cumulative table looks like, hey, I have a date and I have a hard drive model, and I want to know how many failures are happening on that model per day. So basically to do that, we have to take that current data that we just read, right, because that has stuff from today. And then basically what we want to do, so that current, right, so we go hit that current stuff that we just copied, or not that we just copied from the current table, is our cumulative table up here. And that cumulative table could already have basically data from today, so we need to go in and delta scan using DuckDB. We can scan that current Delta Lake table. That's the current roll up basically that we talked about by model and date and the failure rate. You can see there. So we're just getting it for today, where that data at least has the dates that are in this other data up here from this data. And we're saying, hey, give me the records that already exist in this cumulative table for whatever dates we're dealing with in this file that came in. And basically what I want to do is union those two together. So we have all the raw data that came in today, and we're going to get the date, the model, and the failure rates. And then we have the current data that's out there in that cumulative table that we just delta scanned with DuckDB. We union those together. Then we just do a simple group by date model and sum up the failures. So now we have a single line saying for this date, for this model of hard drive, we had this many failures. And then basically we're getting the partitions, so the dates that are in that data set, kind of pull them out with some Python, and then we rewrite that partition in the Delta Lake table and that cumulative table, saying, hey, overwrite that partition with this new data frame. And really all I'm doing here is just showing that it is possible to do fairly complex things with DuckDB and to use Delta Lake. And DuckDB has a lot of integrations for like CSV you saw in this example, or any number of other data sets. DuckDB is nice because it's really lightweight and it can interact with Postgres, CSV files, Parquet files, Delta Lake, anything you could imagine under the sun. We're able to kind of pull those together into DuckDB and do complex data transformations and analytics, and we're able to interact and push data into our Delta Lake. So if we had a S3 bucket where these files are hitting every day, this is super easy to be able to say, hey, ingest this data into our lakehouse with DuckDB and a Lambda serverless, and it's super simple and cheap and cost effective. So yeah, it's pretty cool that you can do that, and you don't need Spark. We didn't need Spark at all to do that. As long as your data sets or your Lambda doesn't run out of, as long as you don't have files that are bigger than 10 gigabytes, which how many people are getting flat files bigger than 10 gigabytes, you should be good to go. This sort of setup's pretty nice. Next, we're going to jump over to Polars, and we're going to basically do another data pipeline in Polars using Lambda, just to kind of show actually a different kind of way We can interact with Delta Lakes with polars inside of Lambda. Polars is nice because it's built with Rust. It's super fast, data same centric, even though it does have SQL abilities. And yeah, this Rust-based polars data frame tool is super fast and awesome. So in this sample, we're going to kind of do the opposite we did with DuckDB. We're basically going to use a sample bike sharing data set that's open source. Divvy Bikes, go look them up. They have an open source data set, and it's basically bike rides. So I rode this bike. It was an electric or classic bike, and this is the ride. It started, ended here at these stations, etc. Pretty easy, basically, data set to use. And we're going to do the opposite of what we did with DuckDB. We're going to basically be getting data, from DuckDB. We were getting data into our lakehouse. Let's say we wanted to get data out of our lakehouse and run some analytics on a Unity catalog Delta Lake table. So again, a Unity catalog Delta Lake table, that's a table that lives inside Databricks, and we're able to basically hit that Delta Lake table in Databricks in Unity catalog, pull it out, do some analytics, and then write a file out. So this is a pretty common use case where we have a lakehouse, got a bunch of data, we may need to pull some data out of it, do some analytics, and then maybe push some results to a file that gets emailed or sent to someone somewhere, right? So we're going to kind of see if we can do that sort of thing with polars and see how easy it is or not. Again, I'm not going to show you the Docker file. I can because it's super simple. There's not much going on. The only thing extra we needed here was a Databricks token because we're going to be hitting Databricks. So obviously we need access to do that. Otherwise, the Docker file is super simple. Let's go look at the actual code. Hopefully it's simple, and it is. There's not much here, and that's a good thing, remember, because I'm just showing you how easy it is to use polars like DuckDB, whatever, to interact with your lakehouse, even a lakehouse in Delta Lake, in Unity Catalog, in Databricks. It's easy. This polars code is super simple. We're just setting up a catalog, which is basically a pointer to our Databricks or any Unity Catalog endpoint, as long as we have the token, access token, to get in there. Once we do that, we can set the catalog up. As you see them here, I have a table that's already set up in Databricks called Confessions Default Trip Data, and I'm hitting that table with a data frame. Then I can just write a query on it saying, hey, maybe I want to group by the date and the ride type, meaning like is it an electric bike or normal bike, and get the number of rides from that. I'm actually, it's a timestamp, I guess, of when that ride left. We're getting it down to a date. You can see there I'm just running another query saying group by the date and the ride type and count the number of rides per day, and then write that out to a CSV file in S3 that maybe gets emailed or processed downstream. Again, super simple code. It's just amazing. Most people would probably do this with Spark, and you really don't need to do anything with Spark. There's no reason. Things like polars and Rust, they can work with large in-memory data sets, and look, this is not much code and it's simple. That's a good thing. I mean, this is a super common way of, crunching data in a data lake or a lake house, and, pushing the results out somewhere. It's super easy to do with polars, and it just requires 23 lines of code here, and we're off to the races. That just shows the power of some of these tools combined with AWS Lambda. You have a super lightweight architecture here, and you're able to process data in and out of a lake house with basically little overhead and not much code. And I want to do another, I'm not sure how far I'll go into this presentation, but I really wanted to cover this last example of Daft. Daft is another modern data frame tool that has a nice SQL API to it. And Daft also has support for Unity Catalog, and it's a Rust base, and Daft is known to be very, very fast because it's Rust based. And just to prove how fast Daft is, I wanted to try ingesting a 10 million line CSV file into a lakehouse, into Delta Lake with a Lambda. Because some people might say, oh, this works for small data, whatever, it's never going to work for big data. Well, if we can do it on a 10 million line CSV file, ingest that into our lakehouse, that's a decent sized file, 10 million lines. That's not nothing. It's just one file. I wonder how fast it can do it on Lambda, because then that means there's a lot of people who could start ingesting data into their lakehouse, not with Spark, which is expensive to run on a cluster, but we could do it on a Lambda, which is super cheap, with Daft, and it could be fast. We'll find out. By the way, Daft has support for both read and write of Delta Lake and Unity Catalog tables. It's a super nice tool. Basically what I did is I have another tool called Data Hobbit. You can go look it up in my GitHub, and I made a 10 million line CSV record with it. It's just a Rust-based tool that will generate a bunch of data for you as you need. I made a 10 million line data file, and to prove it, I can jump over into S3 here. If I go to Confessions of a Data Guy and I go to Daft Large Data Set, you can see I have a 1.1 gigabyte output.csv file, which we'll use for our Daft 10 million line records. This is a proof that I'm not pulling your leg. This is real code and it works great. Here's my Daft repo. We're not going to look at the Docker file. It's super simple. This Lambda function is super simple. All it needed was some basically keys to hit S3. You can see me setting up the IO config for S3 for Daft, and then I go and hit that large data set. There it is, 10 million lines in a raw file. And all I do is raw data frame, collect, write Delta Lake, overwrite, write it into the Daft Delta Lake table, write Delta Lake. And it's just a couple lines of code, and it works great. And I timed it, and it took about 3 minutes and 30 seconds for Daft to ingest 10 million records into our lakehouse, into Delta Lake from S3. From a 1.1 gigabyte size file with 10 million records, that's pretty good. That shows that, there's a lot of workloads that you could probably migrate from Spark over into Daft or DuckDB or Polars, and it can totally handle big data. It's fine. This is a good topic to talk about because it's really about, you want to pause for a moment and rethink about how we load data in the lakehouse. We have this Spark mindset where you think you have to load all the data at once. It's just a data glutton. I have to read all these files at once a day. Take everything we got and shove it in. Yeah, that's one way to do it. But we could also rethink about it and say, hey, can we just eat these files 1 byte at a time? As the file hits an S3 bucket, can we just kick off Lambda and read it with Polars Spark or Polars DuckDB or Daft or something else? Just read it in and shove it into a lakehouse table in a bronze layer or raw staging table. Of course we can. We just saw that you can do it easily. So it's really just about a mindset shift of how we process data in the lakehouse, and you can easily use serverless technologies like Lambda plus these other tools like Daft, DuckDB, Polars. They're very powerful and fast. They can handle big data, and Lambdas are super low overhead as far as architecture. They're really easy to manage. It just makes for really simple, clean architecture, a nice way to ingest data cheaply. Probably the last thing I want to talk about, let's skip over some stuff here, but I just want to talk about a real life example of using not Spark to process data in a pipeline. This is an example from actually production, the place I work. We use this, and we have this sort of use case where we have a bunch of data in a Delta Lake table, and we actually, for some machine learning pipelines, we need to kick off a bunch of other pipelines. And it's kind of hard because these pipelines are all built in Airflow. They're Airflow DAGs. They take a bunch of configurations. It's kind of hard. It's like, do I use Spark on a Databricks job to read a Delta Lake because I need the data in there for some configs and kick off all these other Airflow DAGs that are basically other long, complex machine learning pipelines from Databricks. It just seems like weird using Spark to do that. It doesn't feel right. It feels like an anti-pattern. So basically, I built a system where we use Polars to go hit on an Airflow worker we installed on Airflow. We installed Polars. We're able to read a Delta Lake Unity catalog table in Databricks from Polars inside Airflow worker and basically use the results to kick off all these downstream pipelines without having to resort to Spark and wasting money on a cluster to do this. And this is actually real code I'm showing you here from production. This is really simple. It's a Delta reader function. It just takes a path to a Delta Lake table. It could be a Unity catalog table or any Delta Lake table, managed or not. And it basically reads that into a Polars data frame. Very simple, easy to do. Anyone could do this. You can see here is an example of that code where it's, got that path of the Delta Lake table and it's reading it, and it basically is reading that Delta Lake table into a Polars data frame. It's actually filtering that data frame down to a certain job ID because that's kind of how this works. It has Delta Lake table has a ton of different records. We want records from a certain job ID. Once we have those, as you can see here, we filter them down after we've got the data frame. Then we can actually, from inside this Airflow worker, we can take those. We've kind of hidden a lot of code here, but basically pulls out a bunch of those records, iterates through those records, pulls out certain pieces of those records, certain columns, builds a kind of configuration. And then that kind of kicks off Airflow DAG with those individual arguments. So, you kick off this one DAG and it may kick off 24 downstream model machine learning pipelines. And that's just one example of using Polars with Delta Lake in a real life situation in production without resorting to Spark. So it's very possible to do this. And I think that's where I'll end this talk. If you want to see the full talk, I'll leave a note. Gave it to the Delta Lake community. It's much longer, about an hour long. Kind of go into more in depth, show more code and examples. I actually show some of these tables in Databricks, etc. So if you're interested, go check out that talk. But I hope you found that interesting. And kind of the idea is you don't have to use Spark all the time, especially in the Lakehouse architecture. You can use things like AWS Lambda, which are cheap and easy to use, and you can combine them with tools like DuckDB, PolarStaff, etc. to do a lot of data processing. It's just a mindset shift. So thanks for your time.